guys, if you find this video helpful, please like, subscribe and press the bell icon for notifications. Hello guys, today we will be doing inverse of a matrix. So first let's prove A times adjoint of A is equal adjoint of A times A is equal determinant of A times I. So to prove this, let's take a 2 by 2 square matrix with elements A1, A2 and B1, B2, and now find the adjoint of A, which we can do by interchanging A1 and B2. So write A1 in place of B2 and B2 in place of A1. Now change the signs for B1 and A2. So A2 will become minus A2 and B1 will become minus B1. Now let's take left hand side, that is A times adjoint of A, which will be A, A1, A2, B1, B2 times B2 minus A2 minus B1, A1. Now we have to multiply these two matrices. For that, let's take first column of second matrix and first row of first matrix, and now multiply A1 with B2, then plus A2 with minus B1. So we will get minus A2 B1. Now take the second row and repeat the process again. So we will get B1 B2 minus B1 B2. Now take the second column of the second matrix and first row of the first matrix and multiply A1 with minus A2. So we will get minus A1 A2, then plus A1 A2. And now take the second row of the first matrix and multiply B1 with minus A2 and plus B2 with A1. Now A1 A2 minus A1 A2 got cancelled. Similarly B1 B2, they also got cancelled. So we will get A1 B2 minus A2 B1 0 0, A1 B2 minus A2 B1. So now we can factor out A1 B2 minus A2 B1. Now A1 B2 minus A2 B1 is the determinant of matrix A, and 1 0 0 1 is the identity matrix I. So therefore A times adjoint of A is equals to determinant of A times I. Similarly, we can prove that adjoint of A times A is equal to determinant of A times I. Now since A times adjoint of A is equal determinant of A times I and determinant of A times I is equal determinant of A, now divide both sides with A and we will get adjoint of A is equals to determinant of A divided by A. Now divide both sides with determinant of A and we will get adjoint of A divided by determinant of A is equal 1 by A, and 1 by A can be written as A inverse. Therefore A inverse is equal to adjoint of A divided by determinant of A, and this is the inverse of a matrix. Now for A inverse, matrix should be non-singular. So non-singular means if determinant of a matrix is non-zero, then it is non-singular. And if determinant of a matrix is 0, then it will be singular matrix. So for singular matrix, determinant is 0. Therefore, for A inverse, matrix should be of non-singular. And if A and B both are non-singular, then AB is equals to BA. Now let's prove determinant of adjoint of matrix A is equal determinant of A square. Now we know that A times adjoint of A is equal determinant of A times I, where I is the identity matrix and it is 1 0 0 0 1 0 0 0 1. Now since determinant of A is a scalar quantity, so it will get multiplied with every element of the matrix, and we will get determinant of A 0 0 0 determinant of A 0 0 0 determinant of A. Now take determinant both the sides and we will get determinant of A times adjoint of A is equal determinant of determinant A 0 0 0 determinant A 0 0 0 determinant A. Now determinant of A times adjoint A can be written as determinant of A times determinant of adjoint A. Now since it is a determinant and each row of this determinant has its own common factor, and that is determinant of A, so we can write determinant of A times determinant of A times determinant of A, and we will be left with 1 0 0 0 1 0 0 0 1, and this is by fourth property of determinant, in which we can take out common factor from each row or column. So here each row has determinant of A as its common factor. So we got determinant of A cube times 1 because it's identity matrix, and 1 determinant of A got cancelled. So we got determinant of adjoint of A is equal determinant of A square. Now before moving on, let's discuss this point in more detail. That is, what's the difference between matrix and determinant when we multiply it by a scalar. So if we multiply a matrix with a scalar quantity, it will get multiplied with each and every element of that matrix. So here it will become lambda a1, lambda a2, lambda a3, lambda b1, b2, b3 with c1, c2, c3. So it got multiplied with each and every element of this matrix. So now here we can say that lambda is a common factor and we can take it out like this. Now what will happen if a scalar is multiplied with a determinant? Then in this case, the scalar will not multiply with each and every element of the determinant, but it will multiply with only one row or one column. So there could be 6 scenarios here. In first one, it is multiplying with first row, which will give us lambda a1, lambda a2, lambda a3, b1, b2, b3, c1, c2, c3. In second, it's multiplying with second row and will give us a1, a2, a3, lambda b1, lambda b2, lambda b3, c1, c2, c3. And in third one, it's multiplying with third row and will give us a1, a2, a3, b1, b2, b3, lambda c1, lambda c2, lambda C3. Now in first one, lambda is the common factor for the first row only. So we can take it out like this. And in second, lambda is the common factor for second row. And in third, it's a common factor for the third row. Now in fourth one, lambda is multiplying with the first column. And we will get lambda A1, lambda B1, lambda C1, A2, B2, C2, A3, B3, C3. Now here, lambda is the common factor for column 1 and can be taken out. In fifth one, lambda is multiplying with column 2 and will give us A1, lambda A2, A3, B1, lambda B2, B3, and C1, lambda C2, C3. Here lambda is common factor for second column and can be taken out like this again. And in sixth one, lambda is multiplying with third column and lambda is common factor for third column. So if determinant of A is equal determinant of lambda A1, lambda A2, lambda A3, B1, B2, B3, lambda C1, lambda C2, lambda C3. Now here two rows, that is first row and the third row, they have lambda as their common factor. So we can take out one lambda from row 1 and one lambda from row 3. So we will get lambda times lambda and then A1, A2, A3, B1, B2, B3, C1, C2, C3. Now if another scalar beta is a common factor for second row, then we can take it out, that beta 2. Then we will get lambda times beta, A1, A2, A3, B1, B2, B3, C1, C2, C3. Now let's prove A times A inverse is equals to I. So for that, let's take 2 by 2 square matrix 1, 2, 3, 4. Then its inverse will be adjoint A divided by determinant of A. So determinant of A is 4 minus 6, that is minus 2. So we can write 1 by minus 2. Now adjoint of A is, just interchange 4 and 1 and change the sign for 3 and 2. So we will get 4 minus 2 minus 3, 1, which will give us minus 2, 1, 3 by 2 minus half. Now take left hand side, that is A inverse, which is 1, 2, 3, 4 times minus 2, 1, 3 by 2 minus half. Now we need to multiply these two matrices. So for that, let's take first column of second matrix and first row of first matrix and multiply 1 with minus 2, which will give us minus 2, then plus multiply 2 with 3 by 2, which will give us 3. Now multiply 3 with minus 2 and 4 with 3 by 2. Now take the second column and repeat the process. We will get 1 minus 1 and 3 minus 2, which will give us 1, 0, 0, 1, which is identity matrix. Therefore, A inverse is equals to I, or A inverse A is equals to I. Now let's prove AB inverse is equals to B inverse A inverse. Please note that it's not A inverse times B inverse. It is B inverse times A inverse. For that, let's write AB times AB inverse is equals to I, because we have just proved that A inverse is equals to I. So here A is equivalent to AB. So AB times AB inverse is equals to I. Now multiply A inverse both the sides. Then A inverse A we can write together. Then it will be A inverse AB, AB inverse, and A inverse 1 will be A inverse. Now A inverse A will give us I, and now I times B is B, and now multiply B inverse both the sides and we will get B inverse, which is equal to I again, and I times AB inverse is equals to AB inverse. So we got AB inverse is equals to B inverse A inverse. Now let's prove inverse of A inverse is equals to A. So for that, let's take a 2 by 2 square matrix 1, 2, 0, 1, and let's find out its A inverse, which is adjoint of A divided by determinant of A, and adjoint will be just interchange 1, 1 and change the sign for 0 and 2. We will get 1 minus 2, 0, 1, and its determinant is 1 minus 0, that is 1. Therefore A inverse is equal 1 minus 2, 0, 1. Now let's take inverse of this matrix, which will be adjoint of A inverse divided by determinant of A inverse. Now to find the adjoint of A inverse, just interchange 1, 1 and change the sign for 0 and minus 2, and we will get 1, 2, 0, 1, and its determinant is 1 minus 0, that is 1, 2, 0, 1, which is equal to A. Therefore inverse of A inverse is equals to A. Thanks for watching.